Hi guys, Mr. Kane here.
Hi guys, Mrs. G.
So conjugate acids, yeah?
Yep.
Conjugates. So every acid gives birth to a conjugate base.
Okay.
When an acid reacts
With water.
it dissociates and it forms a conjugate base. Every base gives birth to a conjugate acid.
All right. You give birth to something opposite to what you are.
Right. And the statement here, the relative strength of a conjugate depends on the strength of the acid or base. It's actually exactly the opposite. So if you had a strong acid,
It gives birth to a weak conjugate base, doesn't it?
Right. A strong acid is going to give birth to a weak conjugate base. A weak acid, on the other hand, is going to give birth to a strong conjugate base.
Okay.
And if we're talking about strong bases, they're going to give birth to a weak conjugate acid. And we're talking about bases, weak bases give birth to strong conjugate acids.
Okay.
So for example, we've got this particular reaction, which happens to be a weak base.
Right. Ammonia. I recognize that.
Right. And I know it's a weak base because it's not a hydroxide of an alkali or alkaline earth metal.
Right.
Right. What we've got here is we've got the equation already. This is going to be my base, so we can write that in. That means that water must be my acid here.
Right, because you got one of each.
And if I look over here, I can actually tell that water's my acid because water has become just hydroxide. It's given up one of its hydrogens.
So it donated a proton, and it donated it to the ammonia.
Right. When water did its acidic thing and donated its proton, it became a conjugate base. And that means that when the ammonia gains the hydrogen, it accepted a proton, it became a conjugate acid.
Okay, because I notice if I look at that from right to left.
Yeah, if I look at it backwards.
Take a look at it a little while.
The ammonium actually donates the proton back to water if I'm going backwards.
Correct. It's losing one.
So that makes it an acid.
Yep.
Which is how we just labeled it.
And we just labeled it a conjugate acid because it's not a pure acid. It's a created acid.
Right.
If you will, created.
Which is why we call it a conjugate.
So in a situation like this, Mr. Kane, the acid bases will always be on the left side of the arrow, the conjugate's always on the right.
Always conjugates on the right.
And you'll always have a base acid on the left, conjugate acid, conjugate base on the right in some way, shape, or form.
Right, because you always have to have a proton donor and a proton acceptor. If you don't have a proton donor and a proton acceptor, you don't have an acid and a base. And just to further our idea of weak and strong, this is a weak base, right?
Yes.
Which means that it gives birth to a strong conjugate acid.
Okay.
Okay. And water, I don't recognize it as a strong acid. It's not one of the ones we memorized.
No.
So it's also going to be considered weak here. And that means that it gave birth to a strong conjugate base.
And I'll tell you what, that conjugate base there, that's King Daddy base. So that's a pretty strong base.
Yeah, that is the definition of base.
Yeah.
Right?
Yeah.
Hydroxide ion. And we're going to talk about the autoionization of water.
Okay.
Doesn't that sound scientific?
Does sound scientific because you've been labeling water acid and bases, so
yeah,
I'm a little confused.
We have been labeling water as an acid and as a base in our problems that we've been doing. So the fun part here is that water is what we call amphoteric species, or a substance that can donate or accept a proton depending on the situation that it's been put in.
Well, that would make sense. We've been labeling it one or the other.
Exactly. So water is what we call amphoteric. In this particular reaction, actually water is doing the donation.
Water donates to the ammonia on the left-hand side of the arrow.
Right. Okay. Which is why ammonium is formed on the right-hand side.
All right.
On the other hand, with this particular reaction, water accepts a proton from the acid.
So now it's acting like a base.
So water's kind of confused. It doesn't know if it's an acid.
Wow.
It doesn't know if it's a base.
So water can donate or accept protons.
And we call that amphoteric.
Amphoteric.
It turns out that there are other amphoteric substances. Don't write these down, guys, because it's not important that you memorize it.
Just a piece of information that you need to know. There are other ones.
Water's not the only one.
Autoionization of water. That we knew. And here's the proof.
Here's the proof. Water plus water. If I put two water molecules together,
one has to act like an acid, one has to act like a base.
And we get hydronium and hydroxide, which means that every time you pick up a water bottle, you're drinking acids.
Ooh, and bases mixed in together.
And so is that why it doesn't hurt us?
Well, I think it doesn't hurt us because if you notice, that's a double-headed arrow, Mr. Kane.
Oh, that is. Okay. So that means that if I were to write a K, an equilibrium constant for the, oh, hey, we have KWs, don't we?
Yes.
There's KAs, there's KBs.
And KW for
This is
water.
KW because water can't decide either way, so I can't label a KA and I can't label a KB.
And it's a heterogeneous reaction, and what don't we include in heterogeneous reactions? Liquids. So
It's going to be less than 1 also.
yeah, it's going to be small.
So that means there's only a small amount of either one of these. And since this is an acid and that's a base and it comes in equal amounts, it's a 1-to-1 ratio, right?
Yep.
That means that they'll neutralize each other anyhow.
Yep. There's just not enough of them to bother you when you're drinking water.
And I can actually label these, right? I can label one as a base and one as an acid, which means that on the other side I can have conjugates.
Right.
Right? The conjugate acid would be the hydronium ion because it has an extra hydrogen to give up. And the hydroxide would be a conjugate base.
Because going from right to left, the hydroxide accepts a proton and the hydronium donates it.
So pure water contains some ions. They occur in equal amounts, equal concentrations.
Yes.
And it turns out that we get an equilibrium expression, and this is an important thing to write down right there.
Yes, you need that.
And right here. Both of these facts. Kw is hydronium times hydroxide
I see
concentration.
an algebra problem coming up somewhere along the line, Mr. Kane.
Do you really?
3 variables, one of them a constant at 25 degrees Celsius. Oh, yeah.
Oh, and this is at 25 degrees Celsius, huh?
Yeah, that's only 25 degrees Celsius.
What is that, room temperature?
Pretty much, yeah.
So anytime we do chemistry, it's going to be 25 degrees Celsius, at least for our purposes.
Yeah, always assume 25 degrees Celsius. Therefore, your Kw will be 1.0 times 10 to the negative 14.
So you were right. We do have some algebra to do here.
Yep. I'm always right, Mr. King.
So what is the hydroxide ion concentration in a 3 times 10 to the negative 5th molar solution of HCl?
Okay, so it's a solution of HCl. That
Which
means water is involved.
Yeah, which means water's in there. So that means I can do this Kw thing, right? I can say that Kw is equal to the hydronium ion concentration times the hydroxide ion concentration, right?
Right.
I know the Kw of water.
At 25 degrees Celsius, 1.0 times, negative, that's
It's always
it
that.
is.
So I know I'm looking for hydroxide, so I must know what hydronium ion concentration is.
I'm assuming the hydronium ion concentration is going to come from that strong acid.
Yeah, because that dissociates completely.
And
So
it's a 1-to-1 ratio, isn't it?
Since it's a monoprotic, right, only one proton, so I am going to get exactly 3 times 10 to the negative 5th molar hydrogen ions, or hydronium ions. So 3.00 times 10 to the negative 5th goes here, times
That's my unknown.
my unknown hydroxide ion. So now I just need to solve for the hydroxide ion, right? This should be simple. My math teacher taught me to divide both sides by 3 times 10 to the negative 5th, and I should get a hydroxide ion concentration of
3.33 times 10 to the negative 10. And that has a molar on it because that's concentration has units, K does not.
right. Okay.
So I'm a little visual learner there, Mr. Kane. Can you do me a favor? I don't get where you got the hydronium ion concentration. Could you write out the reaction of H for me? So it's just do it the shortcut way, the cheapy way. HCl breaks apart completely, right?
Mm-hmm.
H ions and chloride ion. H ions, I need oh, okay, so stoichiometrically it's a 1-to-1 ratio.
Right, the hydrogen ion and the hydronium ion, these guys are one and the same.
They're the same thing,
Right.
but the thing that confused me is they give me the concentration of the acid,
Right.
but I have to put the concentration of the hydronium ion in the problem.
If it's a 1-to-1 ratio here, if the acid is 3 times 10 to the negative 5th, then the hydrogen ion is going to be 3 times 10 to the negative 5th. And since that's the same as the hydronium ion, it's 3 times 10 to the negative 5th.
All right.
So calculate the hydronium ion concentration.
All right, let's see. So we're looking for the concentration of the hydronium ion, which is the H3O+. That has a, okay, so this doesn't give me an identity or nothing like that.
No, it just tells us that the hydroxide ion is a certain concentration.
Okay.
So I actually know the hydroxide ion here.
Right. So Kw, so we need, basically it's an equation. At 25 degrees Celsius. Now Kw we know.
Okay.
It's a constant.
So it's this value here.
Right.
And the hydronium I don't know, so I'm going to leave that as hydronium. But I do know that 7.24 times 10 to the negative fourth is the concentration of hydroxide, so I'm going to divide both sides by that.
And you get 1.38 times 10 to the negative 11 for the hydronium ion concentration.
That's a molarity because it's a hydronium ion concentration.
All right, and I noticed that the hydroxide ion concentration is way bigger.
Yeah, the hydronium ion is 10 to the negative 11th.
Yeah,
this is negative fourth. Hydroxide's much bigger.
Yeah. All right, what is the hydroxide in a 0.45 molar solution of HNO3? All right, this is a strong acid. I recognize it. The 0.45 molar is for the acid, but since it dissociates 100%, the 0.45 molar will also stoichiometrically be the concentration of the hydrogen ion, correct?
Should be, yeah.
Okay, so Kw is equal to, here's my equation that I'm going to use, the hydronium ion concentration times the hydroxide. And since it's a strong acid, at 25 degrees Celsius, I know what Kw is, and I know what the hydronium ion concentration is.
Because this is going to be the hydronium ion, just like you said. So this is going to be 0.450 times hydroxide.
So my unknown is the hydroxide concentration.
Hydroxide is going to wind up being
2.22 times 10 to the negative 14. Ooh, that's small.
That is an extremely small molarity, extremely small concentration. Well, that's because we had such a big hydronium ion concentration.
Yeah, that's a pretty big, that's, yeah.
I mean, hydronium didn't even need to be expressed in scientific notation. It was so big. I wonder if these things have meaning, these concentrations.
I'll bet they do.
I wonder if that means that this is a better acid because there's more hydronium.
Boy, it's going to be a pain in the butt, Mr. Kane, if we have to determine if something's acidic or basic based on 2.2 times 10 to the negative 14. You think there's a better way of doing this?
Yeah, I think eventually we'll learn a better way.
Good. I hope so.
We'll figure it out.
All right.
Matter of fact, at least for right now, the useful information is this. The concentrations of the ions do tell us about acids and base, whether something's an acid or a base. So things that have hydronium ion concentrations that are greater than times 10 to the negative 7th usually.
Okay, those are more, that's more hydronium than hydroxide, correct?
Right, more hydronium than hydroxide. If you use times 10 to the negative 7th as the middle, if the hydroxide ion concentration is less than times 10 to the negative 7th, then it's acidic also.
Okay.
Yeah.
They're both equal to 7 to the negative 7. It's neutral.
It's pretty close to neutral, yeah.
All right.
Okay. And if it's the other situation, if your hydronium ion concentration is less than times 10 to the negative 7th, then you're going to have a basic solution.
All right, so you have more hydroxides than hydronium.
Right.
Okay.
Okay. That's kind of tough to do, though.
Yeah, that's hard.
I wonder, there's got to be a better way.
I hope so. I'm waiting.